So, first question is, that would lead to another fancier EPR argument. It's a little bit harder to state, but not much. You can probably imagine it yourself. We'd get the definiteness hypothesis once again. We'd get once again the hypothesis, Alice has a definite X and Y spin, so does Bob, so does Carol. First question. We're talking about cases where one of them is measuring X spin, the other two are measuring Y. In that case, is the definiteness hypothesis consistent? Does it actually work out so that you can describe it without contradiction? And the answer is yes. Okay? I'm not going to worry about this, but I'll just skip through this because I think that we don't want to get into too many details, but just a little picture here to suggest that there's lots of ways it could happen. And here's a diagram here that gives in picture form all the ways it can happen. We can come back to this later if anyone's interested, but suffice it to say, there's no problem. All we were worried about was if one person does X spin, the other two do Y spin, definiteness will work just fine, no problem. But on the one hand, the definiteness hypothesis works for all the cases where there's one X measurement and two Y's, but there's something else that follows from the definiteness hypothesis, and it's not too hard to see. If the definiteness hypothesis is right, then Alice's particle has a definite X spin, Bob's has a definite Y spin, Carol's has a definite Y spin, likewise Alice has a definite Y spin, Bob a definite X spin, and so on. And when we take the product of those three spin numbers for each of those cases, it's always got to be plus 1. That's another way of putting what we said. Therefore, when we multiply all those things together, that's just what I've done there. I've just taken those 9 terms and mushed them together and multiplied them. Well, plus 1 cubed is plus 1. Now, since they're just numbers, we can write them in another order. I've shoved all the x's out to the front, and I've grouped the y's together. So I've got the x's at the front, y1 squared, y2 squared, y3 squared. Well, I'm just multiplying the same things in a different order. It's still plus 1 is the product. But, okay, there's nonetheless something that we notice. y1 times y1, well, if they're both plus 1, it's plus 1. If they're both minus 1, it's still plus 1. The y squared is going to disappear. No matter whether it's y1 or y2 or y3, that term is going to disappear. It's just plus 1. And so what are we left with? Well, the definiteness hypothesis predicts the product of these definite x spins has got to be plus 1. And the problem is, here's what quantum mechanics says. It says the product has to be minus 1. The definiteness hypothesis predicts by simple arithmetic, I know I had to go over it a bit quickly, but it really is simple arithmetic, that the product of these x spins would have to be plus 1, and quantum mechanics says the product, if you make the measurement, will be minus 1. This is true. This is what quantum mechanics says, and although we can't do exactly this precise experiment, we have every reason to believe that if we could, it would work. The only reason we can't do exactly this precise experiment is just matters of it being a little bit too fussy to get to work in the lab. It's just issues about sort of experimental error. But everything we know suggests that this is basically right. So, in short, the definiteness hypothesis would have to say the product of those two numbers is plus 1. Quantum mechanics says the product of those three numbers is minus 1. The definiteness hypothesis from EPR conflicts with quantum mechanics. Oh dear. Well, what's going on here is that these states, the singlet state that we started talking about earlier on, the GHZ state that we've been talking about here, are what are called entangled states. And we can have some discussion about what this means, but and here's just sort of for those of you who like equations, state written out, okay. But what are some characteristics of entanglement? Well, the first thing, whenever you have an entangled state, you're going to get some correlations. But you cannot understand those correlations as I'm merely ignorant of the detailed facts of this thing and I'm ignorant of the detailed facts of that. The arithmetic breaks down. That's what we've in effect said here. Second, and this is another way of saying the same thing, the correlations are stronger than you could get with any non-interacting classical systems. It is quantum. It isn't classical. And there is a sense in which the whole here is more than the sum of the parts. It may grate on your nerves when some people throw on the word holism, and in many contexts I understand why it grates on your nerves. But there is in quantum mechanics a certain precise sense in which you have something that people are happy to call holism. So, here's a coordinate animation. You can think of these two particles as entangling, okay, and this means that they're getting mixed up with one another in ways that classical physics doesn't quite have ways of making sense of. Now we come to the big question. Well, is there spooky action at a distance here? And I'll tell you up front what I think the answer is. I do not know. Okay? But there are still some useful things that we can say. In other words, there are many views about how all this might be explained, if it needs to be explained at all. It's a big controversy in the foundations of physics, and I would just be one person offering my opinion. My opinion is not special. But we can sort of put the question this way. Do the correlations amount to spooky action in this? Well, it's not clear, but here's something really important. And this is the crucial thing that I would like you to take away from this discussion. You cannot use quantum entanglement to send signals and messages. You can't do it. And it's built into quantum mechanics at a very basic level, that anything that behaves that way is not quantum mechanics. It isn't that you have to get to some exotic part of quantum mechanics to derive that result. It's in there at the bottom. Okay? So when Alice and Bob are experimenting on their distant systems, distant meaning she's in one lab, he's in another, and they might be quite far apart, it's built into quantum theory from the very bottom, from the very beginning, the very rules for how quantum states work, that the probabilities for Bob's outcomes, Bob is making his measurements, are not influenced at all, are not dependent upon what Alice decides to do with her device. She can measure X spin, she can measure Y spin, she can measure spin in any direction she likes, and if that's all she does, she just decides which of those measurements to make, Bob isn't going to be able to tell. Nothing in the behavior of his particles will give the slightest hint which measurement she decided to make. No manipulation that Alice has any control over will make the slightest difference to the local pattern of statistics that Bob gets. And that's built into quantum theory at the bottom level. Okay? Likewise, nothing Bob can see, nothing Alice sees tells her about Bob's settings, and vice versa. So, well, how many have seen this movie? You know, I have a confession to make. I have a crush on Marlene Matlin. But in spite of that, no. Okay? No. There are some real problems with the picture of the quantum universe that movies like this and other such sources suggest. And so that's what I want to say a little bit about. The point that I just made, that nothing Alice does in her lab that she can manipulate can make the slightest difference to the pattern of results that Bob gets, nor vice versa. This is why you can't use quantum entanglement to perform magic. Okay? There are really nifty things that quantum entanglement does, but give you control over stuff going on somewhere else is not one of them. Okay? Even if there are quantum faster-than-light connections, I mean, ones that underlie entanglement as opposed to some other kind that we haven't discovered anything about, quantum theory itself says, you can't use them to send messages. You can't use them to control things at a distance. You cannot use them to perform telepathic communication. Okay? The way that somebody once put it in honor of John Bell, who brought so many of these issues to light, there is no quantum Bell telephone. Okay? There is no quantum Bell telephone. And as I was saying to one of you before the talk, it's not a question of whether there are or aren't psychic phenomena. That's a separate question. Even if it turned out that there are, and I'm not suggesting that any such thing is going to happen, but even if it turned out that there are, quantum entanglement would not explain them. Okay? Quantum mechanics is not the kind of thing that can do that kind of work.